This complex looking patch is actually doing something pretty simple. It's feeding a single number back on itself through a nonlinear transformation. And while at low levels of feedback, this system gives us a single stable number, as we increase the amount of feedback, the system starts to oscillate between two numbers, and then moves into fully chaotic territory. Hello, this is episode 6 of New Uses for Old Circuits, Logistic Maps, and Analog Computing with Serge. Now in the previous video, we fed an audio signal back on itself through a nonlinear transform, and we saw all of the really interesting and bizarre behavior that resulted from that. In this video, we're going to do something very similar. We're going to take a single number and feed it back on itself through a nonlinear transform. That's all the patch behind me is doing. It looks very complicated, and in many ways it is, and we'll get into that. But all we're doing is taking a number and feeding it back on itself through a nonlinear transform. When I was doing my physics degree, I took a course on nonlinear dynamics and chaos, and the sort of quintessential chaotic equation that you learn and spend a lot of time working with is called the logistic map. The logistic map is a very simple equation that you can program on a computer so that you can concretely observe a chaotic system unfold. In this video, we're going to use the Serge as an analog computer to patch the logistic map and observe a chaotic system. The logistic map was popularized in the 1970s by mathematical biologist Robert May. He was looking for an equation to model population dynamics, how to forecast what the population of, say, bacteria in a pond will be next year from the current population this year. To model these population dynamics, he used analog computers. This is the equation for the logistic map, and the one that we are going to patch on the Serge today. We start with a number, x of n, and that represents the population, say, of bacteria in this pond this year. And we take x of n and multiply it by 1 minus x of n. In this case, x of n is always going to be between 0 and 1. We normalize the value to something between 0 and 1, and we multiply it by 1 minus x of n. This is kind of almost like a compressor or something. And the result of this multiplication, we then multiply by a scaling factor, lambda. And the result of that gives us x of n plus 1, the projected population of bacteria in this pond next year. So all we really need to do this computation is a couple of basic mathematical operations. We need to do some multiplications, and we need to do some subtractions. And we'll see the modules that do that for us in the Serge. The other interesting thing about the logistic map is this is a discrete equation. We have a snapshot of this year, and we're computing a value for next year. Being an inherently discrete equation, the logistic map is very easy to program on a computer. But in the continuous world of our analog computer, we're going to need something like a sample and hold to move from continuous time into discrete time. Now, in making this video, I discovered a handful of interesting things because, in truth, patching the logistic map was a lot more difficult than I expected it to be. And part of that is because the Serge is not really a perfect analog computer. It's not designed to be as precise as analog computers used to model physics equations. We'll see in very concrete terms that the analog circuits of the Serge don't give us precise voltage values, precise multiplications, precise subtractions, and things like that. Analog computers are designed to carry out all of those operations to a very high degree of precision. But in the synthesizer, we don't really care too much about precision. We're not so concerned with precise voltage settings. We'll see that a voltage setting can have a lot of analog drift and inherent analog noise, but our brain is still going to, say, perceive it as a single note if it's hooked up to control the frequency of an oscillator. That drift and instability in a single voltage value used to control the frequency of the oscillator is not going to appear to our ears as if there's any problem. It's just going to appear as one single note. And carrying out precise multiplication is never really the goal on the synthesizer either. When you're doing things like multiplication on the synthesizer, you're usually using things like voltage-controlled amplifiers, and you care a lot more about unity gain than, say, precisely multiplying 2.2 times 3.3. But with that in mind, we can still patch the logistic map on the synthesizer to get really interesting nonlinear behavior. We're going to run into issues every now and again where the synthesizer doesn't give us the precision that an analog computer would. But again, we're musicians. We're not actually really looking to precisely compute the results of these population dynamics or something like that. We're simply interested in using the logistic map as an example of a nonlinear system that gives us really weird sounds. Now, before we dive into this patch and break it down operation by operation, I think it's helpful to see what the end goal is. Here we have all of our yellow cables doing our analog computation of the logistic map. Remember that the logistic map is a discrete function. It's computing a sequence of numbers. So we start with one number, x of n here, and we do all of this calculation to compute the next number, x of n plus 1. So for that, we have to use sample and holds to store the current value, x of n, and then all of that gets computed by the system, and then we send in a clock pulse to update to the new value, x of n plus 1, which then comes back. This is in fact the feedback element of the circuit. We're taking a number, x of n, which in this case is going to be stored in the SSG, sending it out to the system to do all these mathematical calculations. This is in fact a nonlinear transform, and we're going to see that. And then taking the output of this system, sending it back to the input of the SSG, and triggering it to update to the new value. Our negative slew here is providing a clock, and all the blue cables have to do with the timing signals. We'll get into the specifics of the timing signals and why we're using two SSGs in a little bit. Finally, we're using the output of our logistic map to control the frequency of a variable Q filter, which we're pinging at the rate that we're pinging the whole system at, so we can hear each new value as it updates. So let's break this patch apart into its constituent elements. So to start, we need to start with x of n, our current value in the system. My orange cable here is going to the scope, and we're just going to start with whatever the current value is in the SSG, which we can see on the scope right now is 2.38 volts. So to do analog computing on the synthesizer, all we're doing is taking constant voltage values that we can read with the scope or multimeter, in this case 2.3, and sending it through different modules to perform mathematical operations. What are some of the most basic mathematical operations? Well, addition and subtraction. And we can use the CV processor to do both of those. We send our value, our 2.3, into the CV processor, and we get our 2.3, and we can add it with a voltage offset here. This voltage offset swings from -5 to +5, but as we add, we're adding whatever this voltage is to whatever this voltage coming in here is. We could also use the CV processor to do subtraction. Set the offset to +5 and invert this voltage, and we're now doing 5 minus whatever this value is. We can add two different numbers together. Let's take out the DC offset and take the value that's in this SSG and go to a separate channel of the CV processor. If we turn them both fully positive, then we're just adding these two numbers, and the result is 4.49 roughly. If we invert one of them, then we're subtracting input 2 from input 1. In this case, we get down to 0.2 volts or something like that. Now, one issue we run into is that the output here is not precisely input 1 minus input 2. Part of that has to do with the little bit of signal loss that comes from the resistance in the patch cables themselves. Another part comes from the fact that these sample and hold circuits droop as time goes on. It's just a capacitor holding a particular charge, and the reality is that charge is going to slowly dissipate over time. So the value held here is not going to be precisely the same all the time. We can see that from the fact that we have a bit of fluctuation here down in the decimal place. There's also a bit of noise throughout the system. And the addition and inversion circuits here on the CV processor are not precise. This DC offset is not precisely plus or minus 5 volts. Part of this is from within the synthesizer itself, and a lot of it is also due to the cleanliness of the power supply you're using. But generally, all of these things are good enough for us as musicians. Let's just look at this single output from the SSG and use it to control the frequency of an oscillator, even in the calibrated volt per octave input. And you'll notice on the scope that our voltage value is fluctuating a bit over time. But even with that fluctuation, if we listen to our oscillator, we'll hear a steady tone. This instability is only really a problem if we're looking to use the synthesizer to solve physics equations. So we have addition and subtraction down. What about multiplication? Typically in a synthesizer, when you're doing something like multiplication, you're looking to voltage-controlled amplifiers. Your VCAs are allowing you to control an audio signal by an envelope, which is basically multiplying the signal by anywhere from 0 to 1, giving you silence or your signal at full unity gain. This already presents us a little bit of a problem. Let's say we were to take our 2.6 volt signal and put it into a basic VCA and control it with an envelope going from 0 to 5 volts. The envelope incoming to the control input of that VCA is squished and normalized. At its peak, it's opening the VCA fully to let the input through fully. So we would expect that our 2.5 volts times the envelope at its peak at 5 volts would actually give us our original signal, 2.5, rather than its mathematically correct result of, I don't know, something, I guess, between 10 and 15. The other issue is that typically VCAs are designed with audio signals in mind. That means that in our Serge, for example, the input to our stereo mixer, our VCA here, has a blackjack, which means that the input is AC coupled. Let's take our 2.5 volt signal and patch it to the input of our stereo mixer, patch the output to its output, and see what happens when I turn the volume up. We don't get anything. Modules used on the Serge to process audio, which is the vast majority of them, have AC coupled inputs, and the whole point of AC coupling is to remove voltage offsets. If I add my voltage offset here to, let's say, a unipolar triangle wave, and put that result into our stereo mixer, we'll see that we get a triangle wave oscillating around 0, even though the output here is oscillating well above 0. The AC coupling is a high-pass filter to remove these DC offsets, and since we're patching with DC offsets, we need to make sure to not use any inputs that are AC coupled. Another issue is that VCAs typically don't have clean linear responses, which is necessary to carry out traditional multiplication. Their responses are usually exponential. Luckily in the Serge, we do have one module that allows us to do clean linear multiplication, and that is the active processor. The whole point of the active processor is twofold: to allow us to process DC signals and to do so using a linear crossfader. So let's multiply two numbers. Let's take our 2.5 from the SSG and plug it into input 2 of the active processor, and we'll take this DC offset, we'll just set it to something, and plug that into the control input of the crossfader. The crossfader is crossfading from input 1, which is 0 because it's unpatched, to input 2. And if we have this offset controlling our crossfade, then we basically get our multiplication, with whatever this voltage is multiplying this voltage. So great, we have multiplication, we have addition and subtraction. Let's try to patch our logistic equation. There are a couple different ways we can go about this. We can start with our x of n, which is here loaded in our step generator, and from that x of n, send it through a CV processor to create the 1 minus x of n term, multiply those two things together through an active processor, and then multiply that result with another active processor through a number lambda. The output of all of that will then go back into the SSG, and we will send a clock pulse to update the system to the new value. We can also do this in a slightly different way by doing a little algebra and multiplying this x of n into this term. So we get, it's the same equation, but represented as lambda times x of n minus x of n squared. Of course, x of n squared is just a number x of n multiplied by itself, which is another thing we can do with the active processor. This equation is actually a little easier to patch, so we're going to patch this one. So we have our x of n, that's great, and we're going to first produce the x of n squared term by taking x of n and multiplying it by itself in the active processor. Next, we have to create x of n minus x of n squared. So let's take the output, x of n squared, and go into the input of a CV processor and turn that negative. And into channel 1, we patch our x of n. And let's set this DC offset to 0. So now the output of our CV processor is x of n minus x of n squared. Let's now take that output and run it through another active processor so that we can generate this lambda times whatever this result is. Now for lambda, we could set lambda using another CV processor to give us a DC voltage, but instead we'll just use the crossfade knob itself because this is going to go from multiplying by 0 to multiplying by 1. And that's going to give us our lambda, which is scaling the result of the xn minus xn squared term. And now ostensibly all we need to do is take the output of this and go to the input of our SSG. And so we have our x of n, the system computes x of n plus 1, and it's sitting right here at the input jack to be stored as the new x of n whenever a clock comes into the sample input. Now in theory, this is our logistic map ready to go, and you can see that it's a pretty simple patch. All we need to do is hook up our orange lead to the scope, to the output of the SSG, and every time we ping the SSG, we'll see the new value that this system creates. In reality, though, we're dealing with imprecise electronics here. And additionally, though it's a pretty simple patch, it is a complex feedback system with a nonlinear transform. This xn minus xn squared term is giving us actually a parabola shape, which is taking the input and running it through this parabolic transformation, giving us a nonlinearity which is then fed back into the system. But in reality, we need to use a second SSG as a kind of a buffer. We have x of n coming out of the first SSG and basically running through this nonlinear feedback system, and we'll take a second SSG to capture the output of the system once it settles down. And then after this second SSG has captured x of n plus 1, we will ping the first SSG to grab that value. So we take the output here, and instead of running it back to the first SSG, we run it into the second SSG. We simply take the output of that second SSG, our little buffer, and go back to the first SSG. And then we have two timing signals which are closely related. I have our timing signal from our negative slew running through two different comparators to give us two different times. And you'll see, and as I sweep our lambda here, which is the interesting control, our scaled feedback amount, we'll see that our buffer SSG updates first and then sends that value to the first SSG. You can see it right there. So we have these interrelated timing signals. The final problem is with the range of lambda itself. We need this range of lambda to be somewhere between 3 and 4 to see the chaotic behavior that the logistic map is known for. But our active processor is just giving us an effective lambda of 0 to 1, just taking the input and either defeating it or going to unity gain. The crossfader all the way open is only ever going to really represent multiplication by 1. So we need to take the output of this signal and amplify it somehow. The way I've found to do that is to basically abuse CV processors to take the output of our multiplication here and run it through multiple channels of the processor simultaneously, all at unity gain, basically adding the input to itself 3 or 4 times, which gives us amplification by 3 or 4. Let's turn the camera a bit so you can see the dual processor basically taking these inputs and adding them all together. And I even have 2 dual processors ganged together. And so by taking the output of all of these simultaneous additions and going back to the input of our buffer SSG, we complete the circuit, and now we can watch the logistic map in action. Now let's use this sequence of numbers generated by the logistic map to drive an oscillator so we can hear the logistic map in action. We'll take our output and use it to control the frequency of an oscillator, and then we'll just listen to that oscillator. The clock rate is updating the system with every clock tick. Basically, you can think of it as giving us the new population each year in the population of our bacteria in our pond. Right now, we're in this pretty steady state where every year the population of bacteria in this pond is roughly the same. As we increase lambda, Then the population growth kind of rings around for a little bit, but then settles down again to a steady state. Let's increase lambda a little further. That's weird. We expected it to settle down to a steady state, but it's not. It's now just oscillating around 2 different points. Time marches on, and year after year, the population of bacteria in this pond seems to be swinging between 2 distinct values. Let's turn lambda down again. And down here, the population is settling down again to a constant rate. Let's turn lambda back up. And it's again not settling to a single value, but 2 different distinct values. This is the phenomenon called period doubling. Let's increase lambda a little further. Here we have 4 distinct states. The period of the system has doubled yet again, from 2 to 4. Let's increase lambda further. And we can increase the rate of time. And see that now the system isn't settling down at all. The system is no longer converging over time to a single value for population, nor is it converging to 2 distinct values or even 4 distinct values. It's never settling down at all. The yearly population of bacteria in our pond here has become chaotic. But at some point we increase lambda enough that it snaps out of its chaotic state. But lower lambda again, and we get back to chaos. From converging to 1 value to doubling. Progressive period doublings until we get chaos. We can of course use this chaotic signal to drive anything we want in our synthesizer. Control the frequency of a variable Q filter and maybe as well as its resonance, and ping that filter from our timing signal for the system, and hear new pings as each timing pulse goes by. So in this video, we've been looking at the logistic map, which is a pretty simple discrete equation that gives us chaotic behavior. As we increase lambda, which is basically the scale of feedback going back into the input, we saw that the system settles at first to 1 value, and then mysteriously starts to settle to 2 separate values, pinging back and forth between them. And then as we increased the feedback a little more, the system settled down to 4 different values. Eventually, we hit a chaotic region where the system never settles down at all and simply streams out a seemingly random procession of numbers. But remember that this system is not random. We can go back to those earlier states very easily by just scaling the lambda value back. We're not patching with randomness anywhere in the system. We're simply taking a number that's loaded in the SSG and feeding it back on itself through a nonlinear transformation. The system is entirely deterministic. If we know that number, we can calculate every single next number in the sequence. We know where we need to set lambda to get period doubling, and we know where to set lambda to get chaotic behavior. So whereas in the previous video we fed an audio signal back on itself through a nonlinear transformation, here we're simply feeding a single voltage value, a single number, back on itself through a nonlinear transformation. And we're getting a chaotic series of numbers that we can use to control any other element in the synthesizer. I've made a lot of allusions on this channel to using the synthesizer as an analog computer, and in this video I really wanted to show the nuts and bolts of how you do that. It's not perfect because the synthesizer really isn't an analog computer, but it can still be used in very much the same way. What does it mean to have patched up a simulation of population dynamics of bacteria in a pond? I don't really know, but that's where the artistic side of you has to come in. What do you want this to say? How do you want to use these sounds? What links do you want to draw between this modeling of a physical process in nature and the resulting sounds? How do you take these sounds and put them together with others in a composition? At the end of the day, what we've got here is a region where the scientist, mathematician part of you can be in dialogue with the artistic part of you. And through that dialogue, create something really exciting and meaningful. Before I end this video, I wanted to mention that my friend Sean O'Sullivan and I have recently restarted our podcast from a few years ago called Basecamp Beta, and we've taken it in a bit of a new direction where we're interviewing artists. This week we had on our friend Greg Zifkak, and it was a really interesting conversation about this very thing we've been talking here about, the merging of the scientific mind and the artistic mind. Greg did some similar work and documented it very well on his website, which I'm going to link below. And I'll also link to the podcast episode, which I think you would probably enjoy if you enjoyed this video. So bye for now, and see you next time.